Look back at what I did.
Alright, so I mean, looks like we'll have to figure this out next time because I don't want to waste too much of time. So yesterday it worked for me, but somehow it doesn't work. So, alright. So last class we looked a second time at greedy algorithms for spanning trees. Right, so when we said that when we looked at Kruskal's algorithm, and we also saw an introduction to the max flow problem, right? So we defined what the max flow problem is. And the problem is basically the following. So you're given a directed graph with each edge having a certain capacity, and you want to find the maximum amount of flow that you can send that respects all the capacity constraints. Okay, and we have an intuitive definition for what it means to be a flow. So we had a graph in which you have source S and a sink T. I said imagine a communication network where every edge is kind of a channel and it has certain capacity. Okay, so it has a rate at which it can send messages. And your goal is to find out, so you can route along this path, for example. You might have a different path which overlaps with some of the edges. There are some other edges that you don't use, and so on. Okay, and every edge has a capacity. Okay, and your goal is to pick a subset of these edges. Like maybe you pick this path, and you choose to route, let's say, 2 units of flow along this path. Okay, so this whole path you'll add 2 units of flow. And maybe this edge still has some capacity left. So maybe the capacities are like 5, 3, 1, 2, 2, something like this. So now this edge is filled to capacity because it has capacity 2, and you already have a path of size 2, of value 2, and now you can still route more flow, right? So suppose this path has capacity 1, this has capacity 2. So what more paths can you route? I mean, how much more flow can you route? And why is that?
Because from the source there are only 1 and 1, which is 2 out.
Right. So 2 is an upper bound, sure. So can you actually route 2? Yeah. Okay, so you'll observe that this is one path, okay, where I can route 1 because every edge along that path has at least 1, and you'll also see that this is another path. Okay, and now I've got to be careful because I've got to check that this edge, which is being used by 2 different paths, the sum of the values of the flows on those 2 edges must be less than or equal to 5. And that's good for me because 5 is pretty conservative, so 2 plus 1 is less than 5. Right? So this is what we saw last time. We said that this way of looking at things leads to a natural greedy algorithm. Okay? And before that, so let's formalize what we mean by flow. This again I said last time, but I wanted to go through it again. So a flow is basically a collection of paths, okay, and along with a value for flow along each of those paths. Okay. So in this example, we had 3 different paths. Okay. So the first part, 3 of these orange things, and the first path had value 2. This path had, or I will interchange calling it value and flow. Okay, so first path had flow 2, second path had flow of 1, third path had a flow of 1 also. Okay, so that was this example. Okay, so in general, a flow is a collection of paths, and it has a flow along each path. So that's that. And the main constraint that you've got to respect is that capacities need to be respected, which basically means that total flow along every edge is less than or equal to the capacity of that edge. Okay, so this is capacity of edge. Okay, so this is what we want to do. And I wanted to mention a slightly different way of looking at it, but is this notion clear? So this is what I mean by flows, at least for the purpose of this lecture. Okay, but I want to introduce a slightly different way of looking at it for purposes of the next lecture. So, okay, so another way of looking at it is, you can forget about paths. You can only think of how much flow you're sending across a particular edge. Okay, so what I mean by this is, let's go back to this example where let's say you had S and T, and I had some path like this. Okay, so this was capacity 2, 2, 3, 1. Okay, so this is a very easy example, right? So here, no, maybe I've got one more. Okay, so what I can do is I can say I'm sending 1 unit like this. I mean, you can figure out that there's a flow of value 4. Okay, so it's the same as what we saw before. Okay, so now I could alternately just say, forget about paths, forget about flow paths. Okay. Instead, I'm just going to tell you that there's a flow of 2 on this edge, flow of 2 on this edge, flow of 1 on this, and so on. Okay. I'm just going to tell you the flow value on each of the edges. Okay. And I want to say that using this, you can come up with an equivalent way of describing flow paths. Okay, so it's equivalent to the previous way of doing things. Okay. And this is true as long as one constraint is satisfied, which is what I call flow conservation. Okay. So I could always give some values of flows for the edges, right? Like I could say, oh, this edge has a flow of 2, this edge has a flow of 1, this edge has a flow of 2, and so on. Okay, so let me give an example which you would intuitively see is not good. Okay, so this edge has a flow of 2. So these are not capacities, these are the actual flows that I'm writing down. Okay, so these are the FE values. Okay, so these were the capacities. So now, is this a valid flow?
No.
Okay, and why not?
That middle one is 2.
Yeah, so you realize that, for instance, in this edge, at this node, there's 1 unit of, 2 units of flow coming in and only 1 going out. And that's not valid. Okay, so that's, so that is one condition you can try to enforce. Okay, so you can say that at every node apart from the source and the sink, every node other than the source and the sink, okay, total flow in is equal to total flow out. Okay. By total flow in, I just mean the flow on incoming edges. Okay. So that's what we mean. So this is one way to formalize the notion of flows. Turns out this is exactly equivalent to the previous way. So the previous way, you could imagine it as being pretty cumbersome because you would need to come up with a whole bunch of paths. So describing the flow itself is a complicated thing because you've got to say, oh, I have all these paths. Yeah.
I'm still looking confused about the difference between capacity and the flow.
So capacity is, it's the total flow that is possible on that edge. Okay? And the flow value is the amount that you want to send on this edge. Okay? That you plan to send on this edge. Okay? And I'm just saying that if I have values FEs that look like this, where there's 2 units coming in and 1 unit coming out, it does not correspond to an actual flow in the network from S to T. Because by definition, an ST flow has flow balanced on every node other than S and T.
So no loss.
There's no loss. Yeah. So it's yeah.
Does that also mean that nodes will be assigned capacity and edges will be given flow? Like
No, so nodes don't have any capacity, right? There's no limit on the amount of incoming flow. All you need to have is that the amount of incoming flow is equal to the amount of outgoing flow. So there's no upper bound on how much can come into an edge, into a vertex. Yeah.
So how is this capacity different from the flow?
Oh yeah, so that was the same question. So basically capacity is the total amount of flow that's possible. Okay? That you're allowed to route. It's not, you might not even achieve it, right? So in the previous case, I said there was a edge with capacity of 5. Okay? So imagine if you think of water pipes or something, imagine having like a really fat pipe or something, right? So then you don't have to send you don't have to fill up that pipe with water. You can be sending much smaller amounts. Okay, so that's what we mean by the capacity. It's the maximum amount that edge can support. Your flow might actually be sending much less than that. Okay? So the flow is the amount that you actually are sending. The capacity is the maximum you can possibly send. Yeah.
why can't there be loss? If the capacity is available, so I can have
No, that's the definition of the problem. That you can't. That you've got to have a flow that starts at S and ends at T. Okay? You're not allowed to lose stuff in between. Okay? So that, in some sense, is the definition of the problem. Okay. So any other questions? These are all good questions. So yeah. All right. So good. So now we have the problem set up. All right, and how these views are equivalent is maybe you guys, it's intuitively clear to you guys, but it requires a bit of proof and we don't need it, so I'm not going to go into it. Okay? So if you want to be formal, you need a bit of proof to say that this view is equivalent to the other. All right. So this is what we started off looking at last time, right? So we said that let's consider the obvious greedy algorithm for this problem. Okay, so we said that as long as you have a path with leftover capacity, route some flow along. Okay? So this is what we did in the first example that we saw. Right? So we found that one path, we sent 2 units of flow because 2 was the maximum you could send along that first path. And then you found that there was this other path that I could send flow along, and this one had an edge of capacity 1, so I can't send more than 1. Okay. So I sent 1 along this, and this satisfied all constraints. Then I found that there was another path from S to T. So at every point I have, what I'm formally doing is we have a leftover capacity on every edge. And now you have a new directed graph, and in that directed graph we are just trying to find a path from S to T. Okay. So we have a new directed graph. Which we find an S to T path. And then we are adding that Okay, so is the greedy algorithm clear? So this is basically what we are proposing here. Now, yeah, so the natural question, so does this produce the optimal? Okay, so by optimal flow we just mean flow of largest possible, the largest total amount of flow, right? So remember, this maybe I didn't emphasize as much. Our goal is to maximize the total amount of flow we are sending, along all the paths. Okay, so then, so does this produce the optimal flow in terms of total amount of flow? So what do you guys think? Yeah?
So, what if you find all paths, like all the paths between S to T, and then rank it,
Okay.
and so all the paths, and we for each path we decide that, we select the minimum of the corresponding path, like what is the minimum flow that can go, and then rank this
Okay.
and find where along which path there was maximum flow.
Yeah. Yeah, that's fine, right? So you're basically giving a slightly modified greedy algorithm. You're saying instead of augmenting flow along any old path, just pick the path that would give the maximum amount of flow. That's fine, but my question is, would such a greedy algorithm produce the optimal flow? Or is there any reason? Well, it turns out it's not, right? So I told you, most greedy algorithms don't produce the right answer. So it's just a matter of finding an example, and this one turns out to be a very simple example. Okay, so you have S and T here, okay, and suppose all capacities are 1. Okay. Now what you could do is you could have an unfortunate start, right? So what you could say is, okay, I'm going to do something natural. I'm going to pick this path. Okay. And this path I can route a single unit of flow. Okay. And now I'm stuck because basically if I try to take, now basically I have a graph where the leftover flow looks like this. Now I have S, I have 0, 0, 0 out here, and 1 here, 1 here. But there's no way I can send more flow, because if I look at that path, it has a 0 edge. If I look at any path basically going from S to T, I'll have a 0 edge, 0 capacity. Okay, so now this we are kind of stuck. But instead, if we didn't start with the green path, but if we had started with a path that looked like this, then now you have a different path which maybe looks like this, that you could also have used. Okay, so yeah, I'll pause with this example for a bit, because if you haven't thought about this takes a while to get used to. Okay, so all I'm saying is that the choice of the initial path actually matters. Okay, so if you had chosen the green path, then you result in a graph, then basically you're stuck, you can't improve it anymore. Okay, so you will end up with a flow of 1. Okay, so here the flow equals 1. While the actual max flow is 2, because if you had started with, let's say, the blue path, then there's the other red path that you could have chosen. Okay, so the actual flow, max flow is 2 in this example. Okay. So, could max flow be more than 2? Yeah.
I just had a clarification question.
Yeah.
So we're saying that the flaw with the greedy algorithm is that when it arbitrarily picks a route, it may in fact inhibit other routes.
Yes.
Okay.
Exactly. Okay, because greedy doesn't have a way to pick the right path. Yeah. So what she suggested is one heuristic way to do it, right? You might say the greedy picks the path that gives the best flow. But even that is bad because in this example, all the paths give the same flow. They all give 1 unit of flow. So it's not like one has a better advantage. So, all right. So in this example, can the flow be more than 2? Obviously not, right? And why is that?
Outgoing is only 2.
Yeah. So you have only 2 edges going out of S, so there's no way you can. So yeah, the reason I'm asking this question is because eventually we'll come to a better way of doing the same thing. so I want to. All right. So greedy algorithm can get stuck, right? So that's the bottom line, that greedy can make wrong choices. Now, in some sense, the reason why flow is such an important problem, and this is why all of us study it, is the fact that this is one of the few cases where you can recover from wrong choices. Okay, and that's the algorithm which is, that's the key idea. So this was from Ford-Fulkerson. It's one of the earliest algorithm papers. And what they say is you allow for correcting the wrong choice. Okay, I'll show you what we mean by that. Okay. And the idea is you make some choices, but then you construct a new graph which is called the residual graph. Okay. And earlier the graph I was looking at is I just removed the capacities, right? But here the residual will be something trickier than this. Okay, so this will be a different graph. Okay, so you will construct a residual graph which I will call G sub f. It has a subscript f because it depends on the flow f that we have picked so far. Okay. And in this residual graph, if you can find a flow, then you can in some sense correct for the mistakes in f. Okay, so I'll give examples, but this is the model, this is the high level idea. Okay, so a flow in f, in G sub f, can potentially, or let's say a path in G sub f, can potentially correct a mistake made in choosing f. Okay, this is the intuitive picture. Okay, so now what is the residual graph? Okay, so I want to look at the same example where we failed earlier. Okay, so this is S and T, and all vertices have, all edges had capacity 1. Okay. Now, what is the flow I want to consider? Okay, so greedy algorithm just picked this flow, right? And it sent 1 unit of flow along these edges. Okay, so that's greedy algorithm. Now the residual graph is something, it's another directed graph. Okay, so this I will call it the residual problem. Okay, because I want to emphasize that this is basically another flow problem. Okay, so this is a flow problem on a different graph. Okay, so this is another flow problem, and this is called the residual graph. Okay, and what it has is, first we do what you expect. Okay, so you keep all the edges that you have not used. Okay, so these guys have edge capacities that are the same. Okay, and for the edges that you have used, you again do what you would expect. This is what greedy was doing earlier, right? So you changed the capacities to 0. Okay. But the key new thing you do is you add backward paths. Okay, so So if I have picked this edge from S to, let's say, A, okay, so you add a backward edge from A to S and you give it a capacity of 1. Okay, and you do the same for every edge that you have picked. Yeah.
Capacity of 1 means the old capacity, what it had going the other direction.
No, this is the amount of flow you put on that edge. Okay,
So
so
the amount of flow you put.
you
okay.
put on that edge. Okay, so right, so you could actually the original flow F need not just be one path. It could potentially be like 2 different paths, and then you put an edge whose capacity is the total flow on that edge. Okay. So far this is just a new problem, right? It's not. I mean, I'm just defining a new problem, and now I want to convince you that this finding a path in this new instance lets you find a better flow in the original one. Okay? So that's what I want to convince you guys. Okay? But so far this is just a new problem. Is the definition of this clear? Of the residual instance? I must have a formal definition here. Yeah. So if you have some flow so far, okay, so if you have a flow F, then this residual graph G sub F is a new instance of flow. Okay, so this is a new instance of flow. Oh, my slope. And it has 2 kinds of edges. One is the forward edges. These are basically edges that were already in G. So G was the original instance, right? So for every edge in G, you basically change the capacity so that you make it C of E, the original capacity minus the flow. So this is what we said in this example, right? This is why these edges became 0. Okay, so these were the original edges, and these edges remained 1 because the flow was 0 on these. Yeah.
So had any one of those upper edges been 2, then you would have 1 forward and 1 back?
No, so none of those things can actually be 2, right? Because the capacity is...
No, if they were to, originally.
Oh, you mean the capacity was 2?
If the capacity was 2.
Oh, yeah, exactly. So if you had, actually that's a good point, maybe I should just write 2 here, and then you would have 1 forward and 1 going back. Okay. So yeah, good example. Okay, so you basically subtract for every edge, the forward capacity will be whatever it was, the capacity minus the flow, and then you introduce these new backward edges where you basically say that where you add an edge of capacity F of E, okay, where F was the flow. Okay, so one thing you've got to be careful about, especially if you are implementing stuff, is that the original directed graph could have edges that go in both directions. Okay, so you could have a capacity of 1 in this direction and 2 along this direction. Okay. So in which case, what would you do? I mean, in fact, the residual graph will have edges like this. Right? For instance, you're saying that this one has 1, this one has 1, 2. Like in this example, there's edges going in both directions. So, what does residual mean? What would you intuitively think it means?
Still left.
Sorry?
Still left. Capacity still left.
Yeah, so it's basically what, it's what you would expect, right? So if I had an edge like that, and my green path sent 1 unit of flow here, okay, then the forward edge would get capacity 0 and the backward edge would get capacity 3. So this is how you would implement it. So you would basically have 1 forward edge, 1 backward edge. If you had a flow of a certain amount, you would basically say, remove that from the capacity of the forward thing, add F to the capacity of the back. So this is just a detail that I want to, so if I didn't go into this, I would be hiding this pretty important detail. Okay, Yeah, so let me pause here because this can be a bit confusing the first time you see it. Okay, so that's why I want to pause here and ask questions if some definition is not clear. Yeah.
In the example that we discussed, when is 1 the edge, the back edge becomes 1. When is 2, I mean we use just 1,
Yes.
and then the back edge is 1, is this?
Yeah, back edge is always equal to the amount of flow you send. Okay, so yeah, so in this case, we are sending a flow of 1 along this edge. So the back edge will basically be 1. And yeah, so the forward edge is whatever capacity remains. You will see in a bit why this residual makes sense. Yeah.
Just to be clear, so the forward edge of the residual graph will be the capacity minus the flow that we sent, and the backward edge will be the flow that we sent.
You say that again. So the forward edge.
will be capacity minus the flow.
Yes.
And the
Backward
edge
edge
will
is
be
yeah
the
the flow. Yes. And what I said in this box, the example is that if there was already a backward edge, then you basically increment the capacity of that backward edge by the flow. Okay? So that's all I'm saying. Alright, so this is the residual graph. Okay, so you always add backward edges and you have capacity equal to the new capacity is whatever. Okay, so now why does this have the effect of correcting errors? Right, so let's again go back to this example. Okay, so in this example I told you this is the residual graph. Right, now suppose I ask you to find a path from S to T in this residual graph. Can you find one? Which is, what is it? Yeah, so picture, yeah, the gesture is kind of accurate. So it's something that looks like this. Okay, so you go like this, you take the backward edge, okay, and then you come back. Okay. Now why is this useful? Right? So now look at this green path and that green path. Okay. Now imagine just combining these two. Okay, just superposing these two paths. Okay. So what would you get? So this is a path that travels in this direction. Okay. And this was a path that essentially went in this direction. Okay. Now, if you superpose these two, then what you see is that this edge cancels out. Right? So there's 1 unit of flow here, 1 unit of flow in the opposite direction. So you could say in some sense this edge kind of cancels. I mean there was 1 unit of flow here, there was 1 unit of flow on this side. Okay. So you can define what is called the sum of these two flows. Okay, so I call F, so F was the original flow, let's call this flow F prime. So F plus F prime is just the algebraic sum of the flows. Okay. And in this example it's working out nicely because so if I now look at every edge and look at the sum of the flows, okay, so this edge still has 1 because it was 1 here and 0 here. Okay. This edge now has 0, the middle A to B edge. Let's give names to everybody. Okay. So what you will see is that the sum is a graph that looks like this. Okay, so you have A, B, where's my C? So this was S. Okay, so this edge will remain, so this will have 1. The A to B edge will have 0 because there were two competing flows that cancelled out, one forward, one backward flow. This will have 0, this one will have 1, 1, so we'll have a flow of 1, this will And lo and behold, this is the optimal solution. Right? So this was the flow of value 2 that we initially missed. Right? So, okay, so yeah, just think about, look at this picture, think of adding these two green things in an algebraic sum. Yeah.
So I'm not getting the cancelling out thing. Basically, if you look at this graph, then the sum of all the green edges will be like 1 plus 1 plus 1 plus 1 plus 1. It's not equivalent to like 3 in the previous example. Like,
I will say that again.
so I did not get why you did not consider the edge from A to B. Like, how does it cancel out in this sense?
The edge from it was there, right? So I mean, what do you mean?
So how did can you go to the slide that you were
Yeah. So one of the green paths, okay, so the bottom one sent 1 unit of flow along this direction. The other green path sent 1 unit of flow along this direction. And both of them were paths from S to T. Okay. And all I'm saying is that if I see such a thing, I want to cancel these out and have no edge. It's kind of by design that this is what I'm coming up with. I want to claim that what I get is actually a new flow from S to T, and it actually respects all capacity. Okay, so that's going to be the tip. Yeah.
Then why did you do the same thing for the first edge?
Ah, good. Which edge?
S to A.
So S to A had no green path.
Only green parts.
Yeah. So so greens are, these are the paths I'm finding, right? So in the first step I found that path, next step I found this one. Yeah.
If that is the case, so do they have to be in the opposite direction? Even if they go in the same direction and they are like overwriting or maximizing?
Yeah, then you just add them up. Okay, so if they were going in the same direction, that's a good point. So if you, for example, you could have had, somehow there was maybe a path that went like this, and maybe you're using that 2 edge coming down somehow probably. Okay. Then you would actually add the AB thing and you would make it 2.
So basically, we will go forward only if the forward edge has some capacity left, and we would so only if some capacity is left, then only we will use the forward edge, basically, right?
Yes, exactly. Okay. So right. So now you're getting into, you're basically trying to see why this would work out, right? So this is what I want to say here. Okay. So what I want to say is, let's look at, so this is going to be the claim, which is, consider any flow in the original graph, consider any ST flow, valid ST flow. What do I mean by valid?
Respects capacities.
Yeah, it respects capacities. Okay, in G, and consider the residual graph. G sub F, okay, as defined earlier. Now, let F prime be a flow, a valid flow in the residual in G sub F. Okay. So this, in this case, in the example, F was that green path, F prime is this green path. Okay? And this path looks messy, but it is what it is, right? So it is a valid flow in this new graph. So let F prime be valid from G sub F. Then I want to say that F plus F prime is a valid flow in G. Okay. This is the first claim that I want to say. And furthermore, F plus F prime has flow value equal to flow value of F plus flow value of G, of F prime. What I mean by this is, in the previous example, for instance, that was 1 unit of flow, this was 1 unit of flow. Right? So I want to say that the sum of these two is 2 units of flow. It's a valid ST flow in the original graph, and it's 2 units of flow. So that's the claim. Okay, so any questions on the claim? Okay, so before we prove this, yeah. So any questions on the claim?
Does the superimposed graph gives us the final output, the path we have traced to get the maximum?
Yeah, so the final output will be you keep doing this until there is no flow in the residual.
So in this case, only two flows are there and the
Oh yeah, actually this is, what I should do is, let's look at this final flow. Okay? So this is final flow which is F plus F prime. You can write down what is the residual for this flow. Okay, so let's actually do that. I think this illustrates the thing a little bit. Okay, so now you have, so G was this graph. Okay, all capacities were 1. Okay, and the flow I want to consider, which is this F plus F prime. So let's call this a new flow, which is F double prime. And this one has one unit of flow, Fc equals 1. So this is actually, it has flow values 1. Okay, so it has flow value 1. Now can I write the residual of G with respect to F double prime? Yeah, what would that be?
there will be back edge from forward edge.
Yeah, so for each of those edges there will be a back edge. Okay, so this will be a graph that looks like this. So it is S, A, B, C, D, T. Okay. Now S to A there was a forward edge there, and so now there will be a backward edge of value 1. Forward edge has capacity 0. And A to B, what's the situation from A to B? Okay, there's just the forward, right? So there was no flow there. Okay, so the forward edge remains the forward edge. Okay, so this is still 1. And here again there was a backward edge with capacity 1, forward edge with capacity 0. And here there's no edge. Same here, right? So there's a backward edge capacity 1, forward edge capacity 0, and same situation there. And again, forward edge capacity 0. So So this is the residual which I can now call G sub F double prime. F double prime is that flow. So the point I want to make is that for any flow in G, you can write a residual. And the residual now looks like this. Now in this residual, you will realize that there is no path from S to T. Because, actually you can't even get out of S. There's nothing outgoing. Yeah.
So when we are creating this G F double dash,
Yeah.
and we are cancelling out the edge from A to B, are we replacing it like with a proper forward edge now? Like
Yeah,
the
so
previous-
that one had no flow from A to B, right?
uh,
F double prime. Because F double prime already had cancelled out. There is no edge here. You don't see an edge between A and B, right?
No, what I was trying to ask is, are we like when we remove that
Yeah.
in the algorithm, do we replace it with the original edge?
So there is no replacing, right? So you always keep track of the flow at this step, right? So there's two things. One is the G, and the other is the current flow. Okay. So initially the current flow was this single green thing. Okay. And for that flow, the residual was this graph here without the green path, right? Now in this graph you found the green path. Okay. Now you've updated the current flow to be the F plus F prime. So only in that flow thing you cancelled stuff. The G still remains the G. Okay. So only in the current flow you updated the value. Okay. So the new flow you get is just something that looks like this F double prime. It has those edges.
So it's like the original graph will be what it is.
Original graph always remains the original
This
graph.
is like a snapshot of what we are working on currently. Like.
This is the flow that you currently have sent, that you've sent so far. Okay, and only in that flows you will keep seeing. Okay, so that's the best way to think about it, because you don't want to mess with the original graph, keep changing it. Okay. And at every step you build a G sub F, where F is the current flow so far. Try to find a path in that and keep going. Yeah.
Why is there nothing from D to T?
S to T. Oh, I see. Yeah, no, it's there. It's the same thing actually. So, yeah, it should be the same thing. I just didn't draw it because I drew so many, so I missed it. Yeah.
What if we have more capacity layer and we found another path? So
Yeah.
now we have 3 flows. So now we add all 3 of them, or we add the first one and the last one.
No, so there is no first last anymore, right? So you always have a current flow. So the algorithm just looks like this. Okay, so actually let me show you the algorithm. Okay, you start. It looks extremely simple. You start with a flow of 0. Okay, at every step you have the graph G, the original graph, and you have a flow F. Okay, then you say as long as there exists a path F prime in G sub F, okay, update F to F plus F prime. Okay, and then just keep going. So at every step you have the original G and you have the one flow F. Okay, so that's it. Yeah.
So if we don't find a path, so we go back one step and we'll add those, the original graph with the F prime, or like how do we?
So if you don't have a path like this, then the algorithm just stops. It returns whatever F it had at that point. Yeah.
You say F equal to 0, do you mean like the index of the path?
No, but actually I just mean F of E equals 0 for all edges E. So this is like the empty flow, right? So there is no flow from along any edge. Okay. So yeah. So these are So this clarifies the questions, clarify the notation quite a bit. So it's good. Any other questions?
Yes. So you said we leave the graph, we only change the flow, but what about the backwards edges?
Right.
So where are those added?
So to conceptually think about this algorithm, you just think of at every step you compute this G sub f from scratch. Okay. When you literally implement it, you don't want to do that. You actually want to keep updating the residual also, because the graph could be huge. You find one path, and because you've added one path, you don't want to change the full graph again, right? So that's why when implementing it, you might want to be careful. But conceptually, to think about this algorithm, just think at every step, you update the flow, you have some flow at the current step, and you find the residual of the original graph with respect to the current flow. So yeah, good, great. Yeah, so now I think we can go into it. Now we can go look at this claim again. Okay, so let's see. So what I'm saying is, consider any flow f, which is the current flow. Think of it as the current flow in the algorithm. Okay. Now look at the residual graph. Then I'm saying let f prime be a valid flow in this residue. Usually the f prime will just be a path. Okay. But it could even be a flow in itself. Okay, so this theorem is more general than what we really need. So think of f prime as just a path. Then f plus f prime is a valid flow in G. So this is the claim, and it has value equal to the sum of these two values. So yeah. Any more questions on the theorem? Alright, so now actually some of you have already started seeing why this should be true. Okay, so this is true. Basically, proof is actually pretty simple. It's based on just the definitions of the residual graph and so on. Okay, so let's see why. Okay, so okay, so firstly, let's see a proof of why this f plus f prime, this weird summation that I have defined, is actually a valid flow. Okay. And how do we check if something is a valid flow? Yeah, no edge exceeds capacity, and you want it to be so you want it to satisfy these flow conservation type conditions, right? So we have to check two things: flow conservation and is capacities are okay. Now we are saying, right, so f prime is a valid flow in G sub f. Let's check these capacities are okay part. The flow conservation is essentially trivial. Why is that?
Because we are not exceeding the capacity of any of the edges.
No, I'm not talking about B, I'm talking about A. Flow conservation basically actually maybe the word conservation is not clear to you guys. By flow conservation I just mean total inflow into every vertex apart from the source is equal to the total outflow.
Basically, we can go from one node to another node only with the pathway.
Right, but yeah,
so it's conserved in both of them, so it should be conserved in some.
Yeah, so I mean, if you add two flows, right? If you if you have flow conservation in each of those flows, then the sum obviously has to have flow conservation, because this cancellation that we did only cancels out things that go in opposite directions. So those, it's like from one vertex's point of view, there's an edge going out, there's an equal edge coming in. That's the only place where we have cancellation. Okay, and and otherwise they're just two different flows, each of which has conservation. Okay, so that's why conservation is essentially trivial. Okay. So something that needs a little bit of argument is the capacities. Okay, so why are capacities okay? Okay, so how would you start reasoning about capacities? Okay.
we are making sure that the capacities are not getting exceeded, and the only case and if they are, we cancel it out, like the case where the outgoing and incoming are equal.
Yeah, but there's no cancelling out of capacities, right? I mean, in the sense that, see, what you're going to argue is, I mean, you have a flow in the residual, so somehow you've got to use the fact that we are working with this residual now. Yeah.
So like there is that if we are cancelling out something, so like the forward edge is always capacity minus flow, and the backward edge is the flow. So if we are cancelling out we are basically subtracting the both and like just the capacity is left.
Okay, so I guess that's what you also meant to say, right? Okay, I misunderstood you. But so basically, yeah, so what she's saying is, if you had an original flow F that respected the capacity of this edge, so the point is, arguing about capacities can be done on an edge by edge basis. Okay, so that's the first observation you make. Okay, so now let's look at any edge. So this had some capacity C of E, and F had some flow F of E on it. Right? Now in the residual, okay, so this was G, right? G and the F was drawn on this. In G sub F, what we are saying is, oh, there's a forward edge. This guy has capacity C of E minus F of E, and there's a backward edge which has capacity F of E. Now what she said is half correct, right? So what she said is, if in the backward, if in F prime, you had a backward path like this, like we did in our example, like you had something like this, then obviously F plus F prime is good with respect to the original capacity, because F prime was sending something in that direction, in the opposite direction. Then the new flow F plus F prime is F of E, plus F prime in the opposite direction. Okay. So along the original edge it would be minus F prime of E, which is only less than or equal to F of E. And if F was less than the capacity, then so is F plus F prime. So this is fine. But what if F prime is not in that opposite direction? What if F prime was actually along the same direction? Okay, so this is case 1. F prime was in the opposite direction. Okay, so this is the example we saw, therefore it makes sense. But C could actually have been, in the example that he pointed out, the capacity was initially 2, okay, and now there's a 1 left. So we could be using that 1. So why is that also okay? Yeah.
Capacity in the residual graph is going to be C of E minus Fe. So the flow cannot exceed that.
Mm-hmm.
So if you add these two, you will still get something less than or equal to C of E.
Okay, so is this argument clear? So what he's saying is, like if you looked at this example, right? There was originally a capacity of 2. C of E is 2. And I sent 1 unit of flow on it. Now by definition, I am reducing the capacity in the residual to be 1. Okay. Now any valid flow in the residual, because the capacity is only 1, could have put at most 1 unit of flow on it. Therefore, the sum of the two flows can't exceed 2. Okay. So this is why by the construction of the residual, this is almost immediate. Okay. So this is exactly the argument. Case 2 is F prime in the same direction as E. So here F prime has F prime of E is less than or equal to C of E minus F of E, because this was the capacity in G sub F. And just rearranging this means that F of E plus F prime of E is less than equal to C of E. So, and that's it. Right? So this is This makes sure that the capacities are okay, and we already said that the flow conservation is okay. So this means that this is a valid flow. So these two lies valid flow. And there was a furthermore part to this theorem, but actually let me pause here for a minute. Do you have any questions on the proof? Yeah, just that's why I'm pausing. Stay at it. Okay, so just the outline again. So we're just saying, showing that it's a valid flow basically means you've got to check two things: flow conservation and the fact that the capacities are okay. Flow conservation is easy because you're summing two flows, each of which has the flow conservation property. So it's fine. Now, what about capacities? We said that now let's look at how these G and G sub F are constructed. So if I focus on one edge, G has capacity C of E, G sub F has capacity, the forward direction of CE minus FE, backward direction of FE. And any valid flow in G sub F should either have sent some flow in the opposite direction or flow in this direction. If it had sent some flow in the opposite direction, then you're not exceeding the capacity of E because, you're only using less of that edge. And next, if it is sending flow in the same direction, then the amount of flow is less than the capacity, which is C of E minus F of E. Rearranging, you get that F plus F prime is less than C. This is basically the proof. So it's, yeah.
Why is it less and not equal?
What is less and not equal?
Less than sign. Shouldn't be equal.
Which one? There's a bunch of them. Which one?
The second one.
Okay. So, no, so this one was F, you don't have to send the full thing. Like, the F prime need not be equal to C of E minus F of E. C of E minus F of E is the new capacity, right? So, any flow you send will be less than or equal to that. It doesn't have to be equal to that.
In the subgraph.
Yeah, in the residual. Yeah. So good. So this is the proof, and so again the furthermore part is it's actually again it's really simple. So why is the furthermore part very easy? It's almost as simple as the flow conservation part. Yeah.
Because flow well F prime is never negative.
Okay.
Only increasing.
Yeah. Yeah. Okay.
And that is for the termination thing that we finally reach some maximum flow because we are only adding positive.
Well, that's fine. Yeah, but that's not what I'm asking. I'm just saying, if I add these flows F and F prime, I showed that it's a valid flow in G. I want to say that it has value equal to flow value of F plus flow value of F prime. Some of you might think this is just obvious, but yeah.
Yeah, if there is no overlap between F and Fs, then it's trivial, we just add up.
Yeah.
But if there is overlap like the graph earlier, then we cancel out the common part and the intersection part. So this is basically again the sum of those.
No, but you've got to say that how did we define the flow value? So I guess that's what we should get at, right? So initially we defined flow value in a slightly cumbersome way. We said flows are collections of paths, sum of those values is the flow value. Then we had this alternate viewpoint of the world, where we said that flows are just given by these f of e values, where you have some flow on every edge, and all we needed was flow conservation at anything that's not the start or the sink. Okay. In this new world, is there a way to define the value of the flow?
Just the starting nodes.
It's the net flow out of the starting node. Right? That's the amount of flow. Now, if you think of it this way, is it what happens to f plus f prime?
So either you take a new branch out of the starting node, or you add the existing flow into the same edge.
Yeah, so basically f plus f prime literally adds the two, all the flows that are coming in, it's the net outflow from S. Okay? So it's like the net outflow from S in F plus net outflow from S from the source in F prime. Right? That's what f plus f prime literally adds. So this again is kind of a trivial thing. Okay? So it's and here you use the observation that flow value is equal to net outflow in the algebraic sense, right? So if it's an inflow, you subtract it and so on, in the algebraic sense. That's what we mean by net. Net outflow from S. And then it's clear, because along every edge you do an addition, therefore the sum of them is this number. So yeah, so let's continue. So I'm going to let you guys ponder this if this is not clear offline. So I want to just say a little bit about, just say the algorithm once more. Okay. So given we have this, so the algorithm is now extremely simple. Every step you have an f, you construct a g sub f, try to find a path. Okay, so I will call this path an augmenting path because it lets you augment the flow a little bit. Okay. So this is called augmenting path. And we basically set f to be equal to f, the old f plus f prime. So, and this is the algorithm, and this is due to Ford and Fulkerson. So we still haven't argued about the correctness, right? So we want to say that when this algorithm terminates, you actually have the optimum flow. Okay. So unfortunately we don't have time for that this time, but we will see that early next class. Okay. But I want to say a little bit about the running time. Okay. So let's assume that we've shown the correctness. Okay. So now let's see how much running time you could have. So is there a bound on the running time that you can come up with? I think this is what he was getting at, which is every step you at least increase the flow a little bit, right? So can we quantify? So we want to say that, so if you think about it, this is kind of a local search algorithm. Because at every step we are improving the solution a little bit. You have a flow and you are improving it a little bit. Okay, so it's so you expect the analysis to also be like what we did for local search. Okay, so you'd like to say that every step we make some improvement. Okay, so the analysis idea, mimic local search. Where you say that at every step, flow value increases strictly. And then you hope that, okay, the flow value can't be too big, and so I can't take too many iterations. Okay, so this is the usual thing when you talk about local search. Okay, that try to say that, okay, the solution, the final answer is not too big, each time I make a little bit of progress. So I can't,
In the residual graph, can we take flow values as low as possible?
What do you mean?
Like in the residual graph, when we are taking a new path, the flow values of along the edges of that path, can it be like as low as possible, like 0.001?
Yeah, so far I have not said that pick a path that has the largest flow.
So
or
in that
something.
case, there is no bound on running time because keep on doing.
But can you, I mean, is there really no bound? Like suppose I tell you that, oh I see, so you're just saying that, no, okay, so fine. Let's say you don't do something which is obviously bad. Let's say if you pick a path, you pick at least the minimum edge weight on that path. Okay? So maybe you don't try to maximize this minimum edge weight like she was saying earlier, but maybe you just say, oh okay, I pick some path and I send the minimum edge weight. Okay, but at least send so much. Then can you say that there is a bound? Like suppose I even told you that all edge weights are integers from some 0 through c. Yeah, say some big number. So then can you give a bound on the number of steps this algorithm takes?
Basically it is like finding all the paths between two nodes.
Okay.
So once we know all the paths, we can pick one path, then check if the other path is update the graph, then check if the other path is improving it.
Okay. But how long can this process go for? That's what I'm trying to ask, right? So, yeah.
So I kind of a rough diagram, it's kind of large though.
Okay.
You can cap the flow on the minimum between like the edge weights going out of our source and the ones going in if you sum those edge weights between the two.
Okay.
Right, we can't get a flow more than that, we're going to be bottlenecked, so it's not necessarily the main cut, but and we're guaranteed to increase at least one because we're working on integers.
Yeah, so that's the key idea. Okay, so if you're working on integers, if you're increasing by at least one. Okay.
Sum of edge weights.
Yeah, and now what is the bound on the total cost?
Sum of edge weights of the start node.
Yeah, so it's the sum of the edge weights from the start node, like you were saying. So he's saying that max cut is less than or equal to degree of S times C. Okay, max flow rather, is less than or equal to degree of S times C, where C is the capacity, C is the bound on this. Okay, and each step we increment by at least one, because they are integers, right? If you are incrementing by at least one. Okay, so and which implies number of iterations is less than or equal to something like degree of S times C, which is N times C. Okay, so for sure it's less than N times. Now you might wonder if this is like overly pessimistic, right? So actually an aside, so is this polynomial? Yeah, so we'll get to that. Let's see if somebody else. So this is something that usually I have it in the knapsack assignment. This time there was no place, but yeah. So this is a question that you should, you should ask yourself. Suppose I have integers from 0 to c, and I tell you that the running time is something like n times c. Would you consider this a polynomial time algorithm? Would you be happy with yourself?
No, because C can be arbitrarily large.
Yeah, so when we talk about polynomial time, very often we think of polynomial in the input size. Okay, in the size that you take to write down the input. Okay. So now if I have numbers from 1 through c, what's the amount of space it takes to write down the input? Like suppose I have to write down the number 2 to the 100, right? Okay, here I wrote it down using just 4 letters or something, but let's suppose I have to write it out in binary. So how many steps would it take? I mean, how much space would it take? Yeah, you would take 100 bits to write it down. Okay. So similarly, I mean, you can think that any number which is between 0 to c, you can write it with log c bits. Okay. So the amount of space you're taking to write down the problem is something like n times log c, or maybe n squared times log c. For every edge, you have log c bits. So n times c is not quite polynomial in that, right? Because log c could, I mean, think of c as being 2 to the n, in which case this is like n cubed, and this is like 2 to the n times. Okay, so this is actually exponential. So this is the usual problem in these kind of algorithms. So these are called weakly polynomial time algorithms. So they are polynomial if all the numbers involved are polynomial. Okay, but the numbers need not. Yeah.
So you explain that, right? C equals 2 pi and how do you
No, I was just saying, suppose I picked c equals 2 to the n. Then I still take only n cube space to express the problem. Because writing down each edge weight takes n bits, but still only n bits.
Why is it n squared?
Oh, each edge, there are n squared edges, so potentially. So this is a very weak.
Considering forward and backward?
Yes. So yeah, so next time we'll see if it can really take this long. So let's break.